Okay, there we are. Hello. Welcome to you. Thanks as always if you're able to join me for the live stream. It is always very much appreciated. I have some people who have my back in terms of audio and switching my views. So anyway, that's always very much appreciated. If you're watching the video later in the week, hopefully you're having a good week. Yeah, we're in week 10. So we're motoring right along. We're in this class anyway, kind of between uh, heavy lifting around a project. So pretty soon you should start looking at the next project. And in fact, I think I said it last week, but I'll say it again this week. You should just have a regular look at project 2 as you get to work on each week's lab, and look for things that you can reuse out of the labs, because a lot of the labs are going to have things that by design that are designed for you to reuse. So anyway, be on the lookout for that kind of stuff. Um, so I don't have any demos for labs, but like darn near 100% of them were just really, really well done. So I'm glad everyone's kind of, and I think I said this last week as well, but I'll say this again too. That it's great that everyone's kind of settled in, and I think and kind of just got the routine down for this class. So hopefully that's true, and hopefully it's not causing you any stress, but giving you something interesting to look at or consider or toy around with each week, I hope. Okay, so this is week 10. Last week's labs are really, really good, so hopefully that's just what we see all the way through the end of the semester. And then the second project, which I think you will find probably easier than the first project for the most part, especially because we'll be practicing so many of the skills needed for it in our labs, I think. Okay, so the big star of the show this week is signed integers. So not that we're leaving unsigned integers behind, which don't let us deal in negative numbers, but this week we are going to add signed integers so that we finally have negative numbers in play. So you'll see the first item there is binary addition. And there's a reason for that, is because understanding how the computer deals with signed integers in binary, it's very, very helpful to know how to do binary addition. You don't need to know how to subtract one binary number from another. You don't need to know how to multiply binary numbers in terms of the basic math rules. You just need to know how to add binary numbers, and then you have kind of that opens the door to understanding a lot of how Tues complement works. So you see that term Tues complement, and what we are talking about is the system of representation for signed integers in binary. Okay, so you're going to see me. I think I haven't done for this class, so I'm going to switch over and I'm going to draw pictures for a bit. I tried a graphics tablet early on during COVID, and it just was never, I couldn't ever get my flow. So it's just not me to do a graphics tablet. And because I'm left-handed, dry erase boards are terrible because I smear my hand across my writing. So anyway, you're about to see me do pencil and paper work for binary addition. And hopefully I write big enough that you can see. And I know there's a shadow, but that usually is not, I don't think it'll be a significant issue. So binary addition. Oh, and you also get to see my just horrendous handwriting. So adding binary numbers. The basic rules are very, very simple. Oh, that's cool. Yeah, so Linkridge in chat is also a left-handed person. So I forget what percentage of us are left-handed, but there's a number of them. My grandmother and my uncle were both left-handed, which I think was the only lefties in my family. It can be awkward when you do things like writing, because we have to push our writing. Anyway, so adding binary numbers, the basic rules are simple. So let's do the basic rules. I'm just going to do single bits at a time, because you really only need to understand single bits to do binary math. This is math. So Druid says about 10% of the population are lefties. So that's interesting. I like that. I like being among a 10% of lefties, even though there's places where that's awkward. Okay, so we're not abandoning the rules of math, by the way. 0 and 0 is 0. 0 and 1 is 1. We're just reminding ourselves the rule of math when we are representing data in binary. So none of these basic rules is going to be a surprise to you. If we add a 1 and a 0, we get a 1. If we add a 0 and a 1, we get a 1. No surprises for any of those basic rules. It's math rules. The only weird one, which has implications for us when we are working in Tues complement, is binary 1 plus binary 1. So 1 plus 1 is 2. We're not abandoning the rules of math, except for we can't write 2 because we're not using the decimal system, we're using the binary system. So to write 2 in binary is simply a 1 and a 0. All right, that's decimal. So no surprises that 1 plus 1 equals 2, and 2 in binary is 1, 0, right? No 2 to the 0th, 1, 2 to the first, that's 2. So 1 plus 1 is 2, and that's what it looks like in binary. The reason why that's important to us, though, is because you need to kind of recall when you did long math, if you ever did long math. Hopefully most of you did long math because it's useful for this. I'm going to go right to left this time. So let's do it long math style. And remind ourselves what this looks like in long math. So in long math, what we do is we kind of go one column at a time, and then if there's any spillover or carry, then we deal with that. So 1 and 1, the way to do this long math style is to say that 1 plus 1 is 0, carry a 1. And in this case, we're kind of just at the end of the problem. So this, remembering how you did kind of carry math, so 1 plus 1 is 0, carry 1, is very, very useful for doing binary math, so that you remember to deal with this carry. So let's do an 8-bit problem, and then I'll make a new page here. So 2, 3, 4, 1, 2, 3, 4. Okay, so let's do it an 8-bit problem. So we're going to start at the lowest column, just like we do in base 10, right? We always start at the bottom, and then we work our way up to the bigger values from right to left. So 1 plus 1 is 0. Carry a 1. And now we do 1 plus 0 plus 0 is 1. And now the carry is gone, right? Dealt with. And then the rest of them are just going to be 0 plus 0. So we end up with the 2 that we expected to get. No surprises there. Let's do another one. And I'm just going to spice it up a little bit with some extra digits. To see what happens. Okay, so 1 plus 1 is 0. Carry a 1. 1 plus 0 plus 0 is 1. 0 plus 0 is 0. 1 plus 0 is 1. 1 plus 1 is 0. Carry a 1. 1 plus 0 plus 1, so 1 plus 1, in other words, is 0. Carry a 1. 1 plus 0 plus 0 is 1. And then the final column is just 0 plus 0. So that's our answer. We could put this in a calculator and figure out what it is. But anyway, binary math. Um, Always a good chance that a carry kind of falls off the end, which the processor would detect if that happens. Okay, so there is some binary math. Let's do just a couple more. And then we'll get some more practice here in just a bit. So I'm going to add one more rule here for us to refer to. I'll put it over here. Sometimes we're going to end up with a carry stacked on top of two ones. So 1 plus 1 plus 1 is 3, right? Which is 1, 1 in binary. One plus one is 3, which looks like that in binary. But the way to remember this as a rule is that 1 plus 1 plus 1 is 1 carry a 1. So 1 plus 1 plus 1 is 1 carry a 1. Which will help when we get some nastier problems going. So let's try a couple of nastier ones. Will this work? I think it will work if I do it this way. We'll find out. So 1 plus 1 is 0, carry a 1. 1 plus 1 plus 0 is 0, carry a 1. 1 plus 1 plus 0 is 0, carry a 1. 1 plus 1 plus 0 is 0, carry a 1. So now we have 1 plus 1 plus 1 is 1, carry a 1. 1 plus 1 plus 1 is 1, carry a 1. 1 plus 0 is 1. And now we have no more carries bothering us, so now we're just back to 0 plus 0. So there is our answer. You'll see in just a little bit why it's very helpful to understand how signed integers work if you can do binary addition. It turns out that the processor only knows how to do one form of addition. The processor does not distinguish between adding signed and unsigned integers in terms of its circuitry. It's the same operations. So something to keep in mind. Binary addition is binary addition is binary addition. It doesn't matter if they're signed integers or unsigned integers. When they're in binary, addition is addition is addition. And then we have the two kind of weird situations where we have the carry rule. How would subtraction work using binary addition? So you can negate one of your numbers. So if you want to say 1 minus 1, you can just negate one of them and say, well, instead, let's do 1 plus a negative 1 and see what that result is, which will do that, Druid. So we can see how that works. So the whole trick to pulling off subtraction with addition, as it were, is to negate the second number. And then you can use your addition circuitry and get the same result, which I just think is really neat that it works. At some point, some engineer or mathematician, I'm sure, figured it out. Yeah, we'll see it work. So it's quite cool. I'm just going to stay on the paper for now, I guess. Yeah, let's stay on the paper. So Tues complement. There's really only, well, yeah, we'll say there's kind of one primary rule about it. And let me just put them side by side. So the difference between Tues complement and not Tues complement. For us in the sort of software world, Tues complement means signed integers. What we, sorry, made a mess. What we mean by that is that the values can be positive or negative. What we mean by not Tues complement is unsigned integers, which is 0 and up. So this one's still in our world. Signed versus unsigned integers. The processor doesn't care. It does the same math at the binary level for either system. It doesn't care. Where this matters to us is in software when we are doing our operations and interpreting the meaning of our operations. Then in software, it does matter because unsigned integers can never be less than 0, and they have ranges. Right, like 0 to 255, 0 to 655, 35, and then 0 to 4, some gigantic number, right? And we have to then know if we are choosing to interpret Tues complement, then we get different sets of ranges. For 8-bit, how did I write it? Okay. I should say 2. For 8-bit, the range is negative 128 to positive 127. There's a reason for that, and we'll play around with that a little bit to see it. For the bigger number is negative 32,768 up to 32,767. And then for 32-bit, it's some giant negative 2 million and something to some giant positive 2 million and something. I'm not going to write all those digits down. So anyway, the processor doesn't really care about these things, but the software does. So when we are dealing in signed integers, which are represented in this Tues complement system, it has no effect on the circuitry, but it does have an effect on our understanding of the meaning of the information. We can have negative numbers in Tues complement. We don't have negative numbers in not Tues complement, standard binary if you want to call it that. The ranges change. So no surprises there. Probably most of you remember seeing these numbers at some point. Unsigned integers, 0 to 255 for 8 bits. I'm being too lazy to write a whole bunch of digits, and it would be a mess anyway. For 16 bits, we get this range if it's unsigned or not Tues complement, and we get this range if it's signed Tues complement. And we'll just kind of play around with how the processor doesn't care, but our software should. Okay, so there's that. Tues complement. So if we took a value like this one, it's the same. This is decimal 15 in either system. That's not a problem. And in fact, this value is the same. Which is 127. So some of the values are going to come out looking the same in either system. Won't be affected. But now let's look at where things do get kind of funny. What's an easy one to do? So this one is not the same. So there's a hint here about what sets Tues complement apart from what's not Tues complement. If I ask the computer in my software, if I interpret this as unsigned integers, I get the value 128. Unsigned. If I ask in software, if I interpret this as signed integer, then I actually get negative. Right? Yeah, negative 128. So what's the trick? Does anyone know it already, or does anyone see kind of have a guess as to what the trick is? How does Tues complement know when a value is negative, in other words, versus unsigned, which doesn't care? And while you're thinking about it, I will write a couple more that are negative. Nice one, Druid. And O.I. Hernandez got it as well. So the key is this bit right here, which, I've got a different color pen. I don't know if it'll show on camera. So in Tues complement, this bit is the key. If this bit, which O.I. Hernandez in chat points out as the high order bit in an 8-bit value, or as Druid called it, the leading bit, which are both good ways to remember this. So if the leading bit is a 0, it's a positive number. Got my different. If the leading bit is a 1, it has to be a negative number. So the reason why the range of values is different is because one of the bits has to be given up for the sign, positive or negative, which means that the part that can represent the value is only 7 bits in 8-bit Tues complement. So that's the whole trick. If that bit is 1, it's negative. If that bit is 0, it's a positive number. And then the other 7 of the values the other 7 digits are used to represent the value. Now this one's funny looking. Why negative 128 when these are all 0? So we'll look at that next. That's true. So Druid asks, so binary values don't really have any inherent meaning unless we associate them with a data type at the software layer, and that's basically true. These binary values are just 1s and 0s in the computer, and it doesn't really care. It has circuitry that knows how to do rules of combining them and comparing them, but it doesn't care about any underlying meaning to them. So this binary string on the processor is the same as this string of bits. It only becomes meaningful in terms of being positive or negative at the layer of our software, which is kind of interesting, isn't it? Yeah, that's true. Okay, so that bit. If it's a 0, it's positive. If it's a 1, it's negative. So that's the first thing to note. I do have a note there, by the way, about representation in binary versus hex. If we were to convert these values into hex, so this one, for example, in hex would be, what is this, 91. So for my money, I cannot, just looking at it, I don't know without kind of thinking carefully if this is a negative number or not. So these can be represented in hex, but if you want to kind of understand the system of Tues complement, I don't find hex very useful at all, even though we can still represent it in hex. It just, writing it out in binary is very, very helpful. I don't know how to do hex math off the top of my head, And I also can't sort of easily see the high order bit to know if it's a 0 or a 1 when it's written this way. So yes, you can represent them in hex, but we're not going to do that because we will lose our view of the important bit and then sort of the oddnesses. Like how is that negative 128? Okay, we're going to look at that next. How is that negative 128? Okay, so the Tues complement system, which is what we're going to focus on now, and I'm going to write it shorter to save myself time so my hand doesn't get tired. So the Tues complement system. 0 is 0 as always, so no surprises there. But then if we look at the positive numbers, so that's 0, it's simply all. Look at the positive numbers. We know that they're going to do this. 2, 3, 4. I'm not going to write them all because I don't want you to spend the rest of your life watching me write 127 of these combinations. But you get the idea, right? So these are all leading 0 or high order 0, which means that we know they're positive. And this is going to go all the way up to this value. And we can't go any higher than this and still be positive because we'd have to flick this bit on, which if we're interpreting this as 2's complement makes it immediately a negative number. So the range of values, there's the 0, no difference. Positive values, 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 127, and it can't go any higher because if we turn that bit on, it becomes negative. Okay, so here's the crazy part, and I will sort of make a section to do a few translations at the bottom. So how do we know what negative 1 is? We could memorize it, but I've never memorized it because there's a process to get to negative 1 from positive 1. So you don't have to memorize the negative representations. The only thing that you know for certain, by the way, is that the higher order bit is a 1. It's guaranteed that all of the negative numbers have a higher order bit of 1. We can go one more here. Okay, so they all have a high order bit of 1. We know that. We don't even have to think about that part. But how do we then, without memorizing what negative 1 looks like, get to negative 1? Well, there's a process, and it is what is on my, it's line 15 in my agenda that says not plus 1. So you can go in both directions with this process. So if I know I have positive 1, and I want to get negative 1 out of it, then I knot the bits first. So if I knot the bits, that just means I reverse all of them. That's fine. And then I should have written it here though. So I knot and then I add 1. So if I take the positive value, I knot the bits and add 1, what I end up with is the negative value. So let's do the math. It's these two values. So 0 and 1 is 1. 1 and 0 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 is 1. So that is negative 1, which is some crazy stuff. We'll try a couple of others and then we'll go in reverse. So for me, looking at that or looking at it in hex, which would be FF, that doesn't mean a whole lot to me. Like, I guess I could memorize this one. Oh yeah, that's negative 1 when they're all turned on. But it's easier because I can more easily write down positive 1 for myself. Not positive 1, add 1, get the negative number. Let's try positive 2. So if we take positive 2, we not positive 2 to get this, which is literally just every bit reversed. And then we add 1. We get, see, 1 and 1 is 0, carry a 1, 1, 1, 1, 1, 1, 1, 1. We get positive 2. So not too tough. I'll flip the page and I'll do a couple of the bigger ones, and then we'll also go in the other direction. So if you have a positive Tues complement number, you knot it, you add 1, you get the negative number. Let's see if that works in reverse. So hopefully we all remember just from the page flip that come on, camera. There we go. That all ones is actually negative 1 in Tues complement. We know that it has to be negative because this bit is flicked on, but it's hard to kind of just glance at this and think, oh yeah, all the bits turned on must be negative 1. That's just kind of weird. But it's true. So can we get positive 1 out of this? So we do the same process. If we want positive 1, we can take negative 1 if we have it. We can knot the bits. Oops, we can add 1. Sorry, I just drew the line too quick. So if we have negative 1 and we want to know what positive 1 is, we knot the bits, we add 1, and we get positive 1 back out, which I just happen to think is kind of a cool thing. And if the high order bit is not a 0 when I'm trying to get a positive number, then I know I made a mistake. Same is of the high order bit. If I'm trying to get a negative number and this high order bit or leading bit is not a 1, then something's wrong. Has to be 1 for a negative number, has to be 0 for a positive number. Okay, yeah, so Druid is asking about turning 127 into negative 127. Let me see if I understand the question. It is counter. So the thrust of the chat comment is that Tues complement is counterintuitive, and I agree. It is counterintuitive to me as well. I just kind of lean heavily on the rules, but we could do one. So the not plus 1 is the way the Tues complement system works. Is sort of the whittling it down to brass tacks about it. The Tues complement system is designed to work this way. It just is. So anyway, Druid says if we take positive 127, which is this thing, and we knot and add 1, I keep drawing that line. Then we get which it's true is not intuitive because that doesn't look like negative 127. but it is in the Tues complement system, which I wish I had a better answer than that. Since I'm not a mathematician, maybe a mathematician would be better able to explain in different words that would make more sense to some people. But how do I know this is negative 127? Because I used the Tues complement process, as it were. Starting with the positive number, I applied naught plus 1, knowing this is the Tues complement system, and I know what I get out from that is negative 127. And all I can say is it doesn't look like negative 127 to me either. Because it doesn't. Yeah, it just doesn't. In the sort of standard binary versus Tues complement binary, it's just not super intuitive. So the way I can, well, there's two things that help me with this. One is if I'm ever in doubt, so if I know I'm doing Tues complement and I'm looking at a binary string that I know is negative, and I want to know what it means, like, what is this? Or I can just do a random one. So for me, if I'm told that we're doing Tues complement and I see this, then I immediately think to myself, well, it's negative something. That I know for sure. The rest of this, I don't know for sure. I know it's negative something, so I have to go through the process. I have to do the complements thing to get to an understanding of what this represents. So for me, that's, I'm just going to go straight to the not part, right? So 0, 1, 0, 0, 0, 0, 1, 0. We add 1. And we get 0, 1, 0, 0, 0, 0, 1, 1. Let's see, 0 first, 2 squared, 2 cubed. Let's see, 1, 2, 4, 8, 16, 32, 64, 67. That's the only thing that I can do to reliably, sort of for myself, understand what I'm looking at here. Now, I have to be told this is Tues complement. If you don't tell me this is Tues complement, i.e. assigned integer, then I'm just going to count it like a normal binary number. If you tell me it's Tues complement, then I go through the process. Has to be negative. Negative what? I don't know until I not it. I add 1, and now I can get the positive value, which is positive 67, which allows me to go back to the original value and say, well, that had to be negative 67 because of the way this system works. And we'll fire up some software just to kind of look at bits and interpreting them at the software layer. Anyway, so for me to answer this question, this is negative what? I don't know by looking at it. I have to not add 1. Now I get the positive version of that thing, positive 67, and I can say, oh, that was negative 67. And I can go kind of back and forth. But okay, last thing before we maybe switch over to doing software is the cool thing. Well, I'll do it on a couple of pages. So what happens if we were to add negative 67 and positive 67, which is 0, 1, 0, 0, 0, 0, 1, 1. What were to happen if we were to add negative 67 and positive 67? We know what to expect. So let's see if what we expect is somewhere in the ballpark of what we get. We don't worry about what they are when we do the math. So now we just turn on binary math mode. 1 and 1 is 0, carry a 1. 1 and 1 is 0, carry a 1, 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 0. There is this kind of trailing carry here. But it turns out in this case that that's not of a concern. We get 0 out. And yeah, there is a carry bit, but it's um, it doesn't affect our result in this case. So the 8 bits we get out from adding negative 67 and positive 67 is 0, which is true. That's what it should be, is 0. And I know this sort of extra carry bit is somewhat bothersome, but it turns out that it doesn't affect us in any way, although we could go detect it if we wanted to from the E flags register. All right, let's do, so let me, while I'm on this addition thing, so we'll just set up a couple. So for example, if we wanted to do 10 minus 9, well, what we really want to do is 10 plus negative 9, so that we can use normal binary math on the two numbers. So the 10 is easy. 2, 3, 4, 8, and 2. The 10 is easy. The negative 9 is a pain in my rear because I have to get 9 first, which is 8 and 1. So I have to get positive 9 first to know what this is, right? So I can't intuit negative 9. The only thing I know for sure is that there's going to be a 1 here for this negative 9. But if I need to know what negative 9 is in 2's complement for me, I have to start with positive 9. So crud, I don't know what that looks like. But I do know what positive 9 looks like from standard counting. And then I can go through the process. So I can write the not bits out, which is 1, 2, 3, 4, 0, 1, 1, 0. I can add 1 to it. To get this. All right, so there is the negative 9. So I had to start at a positive 9 to know what negative 9 looks like in binary. Here it is. Now I can write that down. And now I don't have to worry about what the numbers are. I just do binary math, basically, right? So 1, 0, carry 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 1, 0. It is often true when you're hand working these problems that you end up with this extra carry bit, which I don't think it probably ever matters, but maybe it matters. I think it doesn't ever matter. We'll say that for now, and then if I'm proven wrong, then I'll just admit that. So there is an extra carry bit that kind of pops out. But if you look at the 8 bits you get as a result, you get a 1 out. So it's pretty crazy that it does that. Yeah, so there's a whole bunch of that kind of stuff. And I'm going to now, no, I'm not going to do any more paper for this other thing. So if you're looking at a negative number, you start with the positive one, not the bits, add 1. This is how 2's complement works. You get the negative version of that number out. You can go in reverse, which is fine, but if you see that you need a negative number, then write down the positive version of it, not it, add 1, and now you know what the negative version is, if you're kind of hand working the problem. Okay, I'm going to switch views and fire up my get my virtual machine so we can look at software a little bit. So for everybody but engineers, these are interesting insights, and it's kind of cool that the way that it works, and it's good exercise for the brain. But where it really matters is when you're writing software and you have the option to interpret data as either signed or unsigned. So let's switch to the virtual machine and look at that. Let me get this cable out of the way. That should be. Well, let me just in case I had anything trailing behind in there. So, all right, so let me fire up a program here. Week 10. So we'll kind of do a little bit of a proving the point. So now we're at the software layer. And let's just do an experiment. So let's move. It's not bothering me about that. Let's move this value into AL and then print it out. We'll look at it in hex. We'll look at it as unsigned. So when we are typecasting to an unsigned type, that means that that high order bit is just part of the normal binary counting system. I'm not sure what that is, but anyway. Anyway, Orion, so this is a class at Butte College in Northern California. You're welcome to stick around if there's anything of interest to see. All right, so we finally have signed integers in the mix. So I'm going to take this same binary string and I'm going to print it as hex, which should be 8 for this upper nibble and 0 for the lower nibble. So it should be $80. As an unsigned 8-bit, it should be 128. And for signed, what would it be signed? So let's work it out. So how do we know what it is? The one thing we know is that it's negative something because of that high order bit is a 1, right? So let's knot it. Let's add 1. And we get, oops, I'll leave that as comments. I don't want to break the software. We get, as our final result, I have to go backwards. So this is 0, carry 1. It's going to be this. Did I knot it? I did. And then I'm adding 1. Oh, that's the number you were talking about, Druid. That's the number you were talking about. That's the weird one, isn't it? Okay, now I understand that earlier question about what in the heck is going on here. So what is this value? It kind of seems to reestablish itself. So it's this. So yeah, that is kind of funny. So methinks that's negative 128. So remember the whole point of this. If we start with a negative, then we will end up with a positive, and we can interpret it that way. So if we start with what we know to be a negative in Tues complement, and we go through this process, then the resultant value, in theory, if we started in negative and end up in positive, in theory, we can just count this as it would normally be. So what this should be is negative 128, but let's compile it and find out. So that one is a funny one, isn't it? Somewhat off-putting that they look the same. So that may just be one that we chalk up to memorizing or using our software to help us with, because the representation doesn't change. But the thing I try to remind myself here is that if I'm in Tues complement and doing this process, the reason why I am, if I start with a negative number, then what I get out, I'm going to interpret as a positive number. So this, I'm going to go ahead and count normally, having taken a negative number through that process, and get. But the same thing's going to be true if I start. Well, no, you can't, right? Does this situation work? So could I go the other direction here, in other words? Can I say this is positive 128 in Tues complement, so what would it be negative? You would. So the answer is you can't do negative 128 in Tues complement. You run out of space. So if you see this value and someone says it has to be negative, it has to be negative in Tues complement. So it cannot be positive 128 because that does not exist in Tues complement. So that one is admittedly a weird one, because we end up with something that looks like the same value when we go through the process. But we just try to remind ourselves, I know it's negative, so I add 1, and then when I get out, I'm just going to count like a normal positive value and then attach that to the negative symbol, and that is what it should be. Crazy stuff. Okay, so there's this stuff. Let me bring up the calculator and see if I can get this next experiment to work. Hopefully I can get this next experiment to work. So let me make this, I'm pretty sure I can change the number of bits, can't I? How do I get it? Oh, here we go. Let's make it 8-bit. Okay, so let's just flick this one on and see what it says. It's not doing it. It's not doing Tues complement, which I'm frustrated with. That is not 128 in Tues complement. So that's kind of irritating. This calculator doesn't do what I want it to do. So we're just going to have to deal with that. I don't know. I give up on the calculator. Let's do it in code. Okay, so, but here's what I want to do in code. I want to talk about sign extension, and not to master the concept of sign extension, but to just get the idea in your head. So let's use an easier value to contend with. So let's use something else. And let's just print it out before we do anything else. What we expect to see on this second one is, let me put a blank line in between. All right, so what we expect to see on the second one, because we did the math earlier, but if we were to go through, we not all the bits, they become all 0, we add 1, so we get, not add 1 gives us 0, 0, 0, 0, 1, which when we come back to the original value, which we know is negative, tells us, oh, it was -1 to start. That's where we started. So this is -1, but we're going to go ahead and compile this just to confirm that that's true. All right, so that is -1. So now here's the weird part. let's move to AH. So what we have in the end is this. So what I've done here is I have extended this value. So I have more or less grown the AL value to cover over AL and AH, which means that it's now covering over all of AX. And you may remember that we did this for division. We simply moved a 0 in there. So that's what I'm doing here. I'm simply kind of expanding AL out to cover all of AX all at once. And now let's see if we still have -1. Some of you may know that we won't. Okay, so this is kind of what we do with division is we put a numerator in AL and then we zero out AH. And the part of the point of doing that is to preserve the numerator value but give it more space. So does this work for Tues complement? When I'm interpreting it as signed integers, does zeroing out AH mean that AX is now -1? The answer is going to be no, by the way. It's 255. Well, why is that? Because this value in Tues complement is a positive value because the high order bit, if we're considering 16 bits, is a 0 all over again, which means that the whole thing is going to be interpreted as a positive number. So what then if we were to just grow AL out into AX basically by filling up the upper half, AH, but flicking on that sign bit so that it's a negative number once again? Does that preserve the -1 but in a bigger space? It does not. So what we're trying to do here, though, is we want AX to be our -1 by kind of extending AL up into AH while preserving the original signed -1 value. So this is what I'm referring to as sign extension. So here's the whole trick to sign extension. You have to actually carry the sign bit all the way through. So if this high order bit is a 1, then they all have to be 1s. You just kind of carry the sign bit all the way up like that. That's proper sign extension. So now AL has had its negative sign bit extended up all the way through and over AH. So now that when we consider AX, it's going to be the original -1. So that's how we grow an 8-bit to a 16-bit value, which we need to be able to do for things like division. We need to do sign extension. If we start with a positive number, this is 127. If we sign extend a positive number, it's the same process. We take the high order bit and we just carry it all the way across the next register up, which looks like this, of course. So now I have sign extended. I have taken that 0 positive sign bit and extended it, written it all the way up and over AH, so that when I go back now and I interpret AX still is a signed integer. It will retain its original positive value. So sign extension, we're going to deal with this more in the near future because we need to know how to do sign extension to do division with signed numbers. So we did sign extension when we did division with positive numbers. I just didn't call it that at the time because it would have been meaningless. But when we move 0 to AH for 8-bit division, or we move 0 to DX for 16-bit division, or we move 0 to EDX for 32-bit division, what we're actually doing is sign extending a positive number, an unsigned number, to give it double its size. We will not do sign extension manually with signed numbers. There's ways to do that you don't have to work it out for yourself. So this concept is a little bit weird. The whole idea, though, is if I start with a signed value in AL and I want to have that same value but interpreted from the view of AX, the next bigger register up, how do I do that? Well, I sign extend into AH so that when I interpret the entire AX, I'm left with the original signed value that I started with, but now I have twice the amount of space to work with. Same thing works if I start with a positive Tues complement, which this high order bit tells me. Then I sign extend by all zeros for it. And when I interpret the now twice as big AX, it will still be the same value, but occupying twice the space, which gives me the ability to do division and also sort of accommodate larger ranges of arithmetic outcomes, if you will. All right, so why did I introduce sign extension? So that you've seen it before. You're not going to be, there's nothing on the lab or in the homework about this week, but I wanted to get it here while we were thinking about these binary numbers in Tues complement so that I can refer again to it later. Yeah, so I'm going to take a sip of water and just give myself a moment to gather my thoughts. So it's a lot to take in. You may now at least kind of understand better why I wasn't doing signed values from the very start. Is because I wanted to give us a ample amount of time to get accustomed to binary, hex, typecasting in HLA, the basic HLA syntax. I didn't want to mess with any of this mess until we'd had many weeks of experience. So now we have many weeks of experience. HLA is a lot less troublesome to us. Typecasting, understanding hex, binary, decimal, and how they're all being used. They're just different systems of representing information. Now that we kind of have all that hopefully kind of tucked away nicely in our heads, I thought now we can start talking about how do you do signed integers, and then we'll start doing experiments with them. But anyway, that's just a way of saying why did we wait until now, is because I think if I had hit you with this at the very beginning of the semester, for a lot of people it would have caused undue pain. So that's why I put it off until now. Okay, so Tues complement, what is it? It's a way of representing negative numbers. How can we use that in our software with the appropriate HLA data types, which give us the interpretation of those bits that understands them to be positive or negative. So that's the whole trick here, is that in our software, we can use signed variables. When we want the Tues complement, we don't really have to worry about the Tues complement stuff. We can use signed typecasting to get the Tues complement, to get the assigned representations out that we want. And we don't really have to worry a whole lot about what's going on under the hood, but it is super interesting, and it does give you some insight into why the ranges are different. Why 0 to 255 for unsigned versus negative 128 to 127 signed, because that high order bit is taken away in Tues complement and used to represent positive or negative. Yes. So Druid asks, uh, asks in chat. So the meaning of sign extension is um, you move 8 bits of ones into the next higher section for negative numbers, or you move 8 bits of zeros into the next higher section for positive numbers, and that is correct. So to sign extend an 8-bit, let's say an 8-bit value in AL. So if you have a negative 8-bit value in AL and you want to kind of promote it up to being a 16-bit value, then you load up all ones into AH. Now you have AX that is bigger but still maintains the original value that you were representing in 8 bits, but now you have extra space to do more work. Also, it's required for doing division. If you have a positive number in AL and you want to promote it to be 16 bits, then you sign extend it by carrying zeros all the way through AH. Now, when you go back and look at AX, it's the same value that you started with, positive, but now you have the 16 bits of space to do work in, for example, division, which is where it will be required. One of the reasons why I'm showing you sign extension, this will be the last thing I'll say about it unless there's questions. One of the reasons why I'm showing you sign extension this way today is because there are x86 instructions that automatically detect the high order bit and automatically copy ones or zeros up for you. So we'll be using those instructions. We won't see the ones being carried for us, and we won't see the zeros being carried for us or copied in for us. But it will be happening when we run these instructions. So when we get to doing signed division, you'll see new instructions, and they will all be related to the problem with sign extension, but they'll be doing the work for us. Anyway, we won't see this anymore, so I wanted you to kind of at least have a sense of what's happening when we start doing division on signed integers. All right, so I don't think I need to write that much any more stuff here. I am going to do a quick example on robust input handling. But anyway, so we now have int 8, int 16, int 32 data types, which are the signed 8-bit, signed 16-bit, signed 32-bit. Their ranges are different because they have a low end in the negatives and a high end in the positives, which is different from unsigned integers. Wikipedia has a good integer for computer science page if you want to go look up those ranges. I don't ever remember all the digits for 32-bit signed integers because it's just too many numbers and life is too short. So just go look it up. But anyway, we have those 3 new data types. We also have three new input handling routines when we want to read in signed values. So get I8, they all still return in A. So get I8 returns a signed integer in AL. Get I16 returns a signed integer in AX. And get I32 returns a signed integer in EAX. And I'm gonna write a procedure and talk about robust input handling here since I haven't gotten to that yet. And then we will use one of those routines. So let's just do a get int 8. Okay, so the basic process, of course, is just standard out output. Enter a value between negative 128 and positive 127. I know that because that's the possible range for 8-bit signed integers in Tues complement. And then I'm going to do a standard in.get I8. And that's pretty much the whole routine. I'm going to go ahead down here, comment these things out. So the whole point would be that we invoke this function, and then we can say you entered And then we're careful here to typecast to the right signed type. Signed 8-bit input, signed 8-bit typecasting, AL. I'm going to put a period at the end. I don't know why. It just seemed bad to not do that. So let's start here, and then I'll just kind of quickly build out a robust input handler using HLA's features to do that. But let's just check it real quick. I'm going to go ahead and put this in a forever loop so that I can break if AL is 0 and that way I can try it multiple times. I'm just going to remember that I have to type in 0 to get this to work, to quit. Okay, so let's build that. All right, so let's go ahead and just try the boundaries. Looks good. The other boundary, that's good. We also usually, when we're doing tests like this, try the edges, -128, 127. Try everything around 0. So -1 works. 0. Oh yeah, that's the quit, dummy. So I can't do 0 because that quits the program. 1, that works. Okay, now let's see what happens if I try to exceed the bounds. So the program crashes and I get an exception that says value out of range. I may have to look this up for myself because I don't write this enough. So what we're going to add to make this program robust is that we don't want these exceptions to crash the program. What we want the program to do is grouse at the user, right? So instead of just crashing the program, let's detect this exception happening at runtime, tell the user you've been naughty, and give them another go at it. So the way we do that is we're going to stick them in a forever loop here. And then we're going to set up for the potential for an exception, which looks like this. And I'm going to do sort of the simple form of it. So this is it. So this try any exception in try. There are fancier ways to do this in HLA, but we don't need them. So basically, I am stuck here trying to get a good value. And instead of letting the program crash on exceptions, I'm using this try setup to capture in my runtime. So instead of crashing, I'm going to be able to handle this problem in the running software. And what I'm going to do is grouse at them. And that's it for now. I am going to add one other piece that's a little bit weird. But anyway, this is the basics of it. Anything that goes wrong with that input, if it's outside the bounds, if it's nothing that can be an I8, those would be the two main ones. If they do an input that's not legally an I8, instead of crashing the program, we're going to capture that exception that would otherwise crash the program, print a nastygram, and then stay inside this loop until we get what we want. Now, the other thing that we need here is a way to get out. So this is going to look funny at first. In fact, there's two pieces of this. So the way to read this, we are stuck here forever until that user gives me something that is legally an int 8. That's what the for loop is for. The try block is there so that if an exception happens, meaning my user has been naughty and they typed in a string or they typed in a giant negative or positive number, something that's totally illegal for int 8, instead of crashing the program, we're going to print out a nastygram and keep them here. So on this get I8, if one of those bad things happens, the program immediately jumps to this exception section. Immediately. So these two lines of code only happen if all goes well with the get I8. Fundamentally, if all goes well with the get I8, we want to just break out of the enclosing loop. We got a good number, we're ready to go. This unprotected thing is an HLA oddity, in my opinion. You don't see this in lots of programming languages. But if you read the HLA documentation, it will tell you that in a try exception handling block, when you get to the good result, this keyword unprotected allows HLA to do some cleanup. And I don't know what that cleanup fully entails, but to a certain extent, it entails cleaning out the eFlags register a little bit and cleaning up some of the registers. I have never gone and looked at the entire technical details. I just know that if all goes well, we need to fire off that unprotected because HLA tells us we should, and then we break. If we don't do this unprotected, we sometimes get polluted data in the registers. So that's why that's there, is because HLA tells us that it needs to be there. The break itself is what I want to do when all goes well with the get I8. So I know that looks a little bit weird, but that's the full sequence of getting a valid input from the user. Let's try it though. So let's do the regular stuff. So we haven't broken any of the normal stuff. That's all good. -1 works. I can't press 0 because that quits. That all works. Now let's start being naughty. So let's try -129. So it caused an exception, but I handled it in software, so the program didn't crash. It jumped straight to that output statement and then continued back at the top of the loop. If I'm naughty on the other end, same thing happens. So it jumps straight to the exception, printed a nastygram, and then the loop repeats the process. If I type in something that couldn't possibly be an I8, let's see what happens. Same difference. So this gives us kind of fully robust user input handling. And if I put a 99 in, then I succeed in getting what is a valid int8 out of that routine, and then I'll do 0. So I know the unprotected is like the least understandable part. You need it there because if all goes well with your input, HLA needs you to call this to do some cleanup for itself. And then you can proceed with the loop break that you wanted to do. We can also, let's do some min-maxing here. So now we'll have a min-max. So the thing to keep straight in your head is that the minimum and maximum values are a separate issue from whether or not it's even a valid int8. This minimum and maximum are whatever the caller sets, but it's completely separate from whether or not I can even get just a verifiable int8. So once I get a verifiable int8, now I can check my min and max. So if AL is greater than or equal to min and AL is less than or equal to max. So I can still do this logic as long as I get this little HLA cleanup, the exception handling call, before I do whatever other work I wanted to do. So this break if only happens if the I8 is a valid I8, and then I can check to see if it is validly in the specified range, which I'll try. So let's do -10 and 10. I should probably be nice and print those things. Okay. All right, -10 and 10, so -11 will be a valid number, but it won't let me get out without it. So -10 should now work. Yep, and then I got back into the main part of the loop, and then if I do void, then the exception handling part kicks in. I could make this fancier if I want to. I could say if those are good, then break. Else, I'll complain about this other issue. I'll say please. See if that helps. In fact, let me just take this and add please to it. So it's a separate issue. So notice again, though, that anything is sort of just the standard range checking logic I do after I do this call that HLA requires me to make that says that I got a valid intake, but I don't know if it's in the range that I wanted. So we'll just try that one more time to make sure that it is functional. So -11, so please don't be dumb. So there we go. Get out of the program. So anyway, I wanted you to have an explanation of that procedure setup. You have one that's fully implemented for you in the lab this week, and I think maybe last week as well. So anyway, now you know why all those pieces are there. This exception handling strategy is common in high-level programming. So C++ has it, Java has it, Python has it. Most languages have some form of, well, not most, but many languages have some form of exception handling where you can capture these otherwise program breaking problems and deal with them on the fly. What else do I got? Week 10 lab tips. I'm just going to switch the views, go look at the week 10 lab, and then I think we'll be done on time today, which is probably welcome news. So project 2 is not till December 11th, but at some point I'll start bothering you about that. Probably next week I will start, or the week of November 7th. Anyway, in the next week or two, I will start pestering you about the second project so that you have it on your radar. All right, week 10, hopefully you are seeing that. You are, okay. So this week, Tues complement. Reversing the sign of Tues complement, not add 1, goes both directions. Binary addition. So the beauty of Tues complement is that the process of doing binary addition doesn't change. The interpretation of the resultant value changes kind of when you take the higher level view and ask yourself, do I want it to be signed or not? I don't know why this bitwise thing is, because we're doing it in the lab. So we're continuing just to practice a little bit on the bitwise operations at the same time. But that's in part because the Tues complement process has a not in it. Okay. So not tons of reading this week. And get the lab queued up. And then I will walk through this thing before I go to the lab real quick and then make closing comments. So one of the sections I think has already started the Who Invented X. You don't have to answer every question all at once. I mean, you can kind of seed the discussion that way, and that can work too. But you can also just pick off a topic and explore that one thing. But anyway, one group is not necessarily both groups will do it the same. Anyway, just kind of where did these things come from? Where did the binary system come from? Where did the hex system come from? Who thought of Tues complement? These things came from places or people and times. So it's it can be interesting to know that it came from somewhere, and who was that, and why and how did they come up with it? Homework lab discussion as always. Project 2, I would just recommend that you go look at it each week, either probably as you're working the lab or at least shortly after you've completed the lab, so you can see if there's anything you can steal and use in project 2. Okay, the lab itself, I'm just going to look at it here. So here is a get number. It's doing a get 8. You'll notice it's got the old unprotected thing in there, which we now at least know is because for whatever reason HLA wants you to do that. And if you don't do it, sometimes it makes your data be wonky. So make sure that after a successful get something in one of these try exception blocks, you do an unprotected before you do whatever work you would do normally. And then you have the exception section, which is what you entered couldn't possibly be what I'm asking for. Print binary and decimal. I think this one's just been implemented for you. Go again has been implemented for you. So let's see what we ask you to do. So number one, so you have to do all the procedures this time. And then I have provided the output section to follow the calculations. So directly below item 1, like right here around line 98, you will compute the sum of number 1 and number 2 using AL to hold the result. Why is that? Well, we don't want to mess up number 1 and number 2 because we're printing their original values out. And then we're printing the result that has been computed into AL out. So be careful that you follow the instructions. Have AL be the receiver of the calculation. Number 2, reverse the sign. So there's 2 ways to do this in actual code. One way is to use a not operation and then add 1 just like we did on pencil and paper. So be careful to not destroy the original values, but you will copy number 1 into AL. You will not AL, you will add 1 to AL. And that would give you, when interpreted properly, the opposite sign, the positive for the negative or the negative for the positive. Number 3 is to use an x86 instruction, which does the whole process for you in one step, which is the negate instruction. So you'll use that one on number 2. So you will move number 2 to AL. You will negate AL, and then this will print out the results for you. And then we'll do some practicing on AND. So using AND with a proper filtering value to clear a nibble. And I'm going to leave those sort of as the challenge component because I want you to be thoughtful about this. If you struggle with how do I clear a nibble using the AND instruction and the filtering value, Canvas Inbox, Piazza, Office Hours are all places to go get help. Piazza would be by far the best for getting help on this lab so that your classmates can participate with you in working out the solution to these parts that have this sort of challenge component. So it turns out that if we AND a value with a well-chosen filtering value, we can actually zero out an entire nibble. Let's see, ORing. So here we actually just wipe out whatever number 2 used to be. And then in the ORing section, we're going to use the OR with a filtering value to flick on specific bits in number 2 to get practice with that. So using AND to clear bits, using OR to set bits is the challenge. And then using XOR to zero things out. The trick to XORing to get 0 is XOR a thing with itself, and then you get 0. Okay, so I'm not giving you nearly as much of the possible solutions there. So I hope that you will make use of Piazza if you get stuck on any of these and help yourself and your classmates get to the solutions. But if those aren't working out, then Canvas Inbox, Piazza are available as always. So these are a little bit more thinky problems to continue practicing with bitwise operations at the same time that we are beginning to incorporate signed integers into our work. Okay, so that's that, I think. So I'll sit here for just, it's 2:29, so I'll sit here for the last minute and just wait and see if if there are any questions. Worst comes to worst on the lab, you just try a bunch of stuff until you get the desired result. Or you take pencil and paper and kind of work out manually what it should be to get those solutions. So that's it. Hope you have a great week. I find this stuff interesting. I hope that at least the larger number of you find it kind of interesting to put your brain to these kinds of problems. There are times when it is useful to have a sense in your head when you are doing high-level programming of what it means to have a signed integer, what its limits are, especially versus an unsigned integer and what its limits are. But now you have a sense of how they work on the processor as well. Thank you, Druid and Linkerage. You guys have a great week as well. I'm out there if anyone needs help. I check Piazza every day, Canvas Inbox every day, office hours as always. So anyway, be in touch if you need any help. Otherwise, I hope you have a very good week, and I will see you on Tuesday afternoon next week. So thanks a bunch if you could join me for the live stream, and thanks a bunch if you're watching the video later. It's nice to know that it gets consumed by somebody, so I appreciate that.